we are going to find the eigenvalues and then the corresponding eigenvectors for this 2x2 matrix. So first, we'll always set up this lambda I minus A matrix. So that's going to be lambda times the identity minus our A. And so the lambda I is always just the diagonal matrix with lambdas. And so if we clean this up, we will get lambda minus 1, -5, -3, and lambda minus 3. And so to find the eigenvalues, we are going to take the determinant of this. And so that's it's 2x2, so it's just going to be top left times top right minus the other diagonal. So we're going to get lambda squared minus 4 lambda plus 3 minus 15. So lambda squared minus 4 lambda minus 12. And hopefully it factors. This does. It'll be lambda minus 6 and lambda plus 2. And basically what we do is set it to 0. So that we get our solutions at 6 and -2. And now to find the corresponding eigenvectors. So I'm just going to create a little space. So at lambda equals 6. So basically what we do is we find the null space when we throw this back into the lambda I minus A. So lambda I minus A is going to be, I'm just going to throw it in here. So lambda minus 1 is 5 and -5. And I'll have -3 and 6 minus 3 is 3. And so we want to get the null space. So because we're in a 2x2 matrix, what we should find, if we have an eigenvalue, this has to have a non-trivial null space. And the only way that happens is if one row is in fact a multiple of the other. So we should be able to check that, and I have that here. And then a really quick way that I can actually generate a vector for a 2x2 in these cases is to just kind of flip the two entries around. So I have 5 and -5, so I'm going to write them in the opposite order. And then what I'm going to do is change one of the signs, not both. And by doing that, that's going to guarantee that the product, 5 times 5 plus -5 times 5, it's going to guarantee that that is going to give me 0, so that this vector over here is in the null space. But I can actually reduce that a little bit and get something nicer. I don't need 5 and 5. I can just divide the thing by 5. And I can get the corresponding eigenvector here for 6. Now I'll call that lambda 1 to be just 1 and 1. So that's going to be my eigenvector for lambda 1. And then similarly for my second lambda, -2, I'll get lambda 2I minus A is going to be, so just be careful with the negatives, but I'll get -3 and -5 and -3, and that's also -5. And again, the rows should be a multiple of each other, and they're in fact the same. And I'm going to do this trick again. My x2, I'm just going to take the same two numbers, -5 and -3, so I'm going to change their order and then make one of them positive. So I'll just take the first one instead of negative. I'm going to flip it to a positive. By taking the same two numbers, you guarantee that the products of each pair, like -3 and -5, is the same as -5 and -3. And so I flip one of the signs so that they take away from each other. And so we can check that this works. I get -15 plus 15. And so yeah, that's going to be my second eigenvector. And that's what we were asked for here. So these are my answers.